upcoming slides. So these kind of the innovations even you can use in your lab also using any traditional CAM softwares. So that we'll discuss in the upcoming slide. Like that, why manufacturing is mostly preferred because it is actually picture. You can see this trunk of this tree where you can see all the layers are visible. It's growing from the core and it's growing in the outer direction, and you won't see any wastage in the nature. Similar to additive manufacturing, the wastage is quite minimum. I can say like in certain cases it will be zero wastage also. And yeah, since we have designing, so we can go mass customizations. We can make very much complex shapes. Like you can see, all these parts are printed in our lab using different printers like powder bed fusion. The ascending order of energy. Fat preparation being the least energy, while the direct energy deposition consumes the maximum energy. So, like you can see, the fat pyramid is nothing. It's a DLP, like digital light processing, or it's like SLA, mostly popular in such processes. So, even you can make your own DLP system using a normal laser pointer that we use in during presentations. So, we using the set some same energy only, we can use a of fat polymerization. But when it comes to the metal, we need much high energy. Therefore, in metal, basically, we use this direct energy deposition process and powder bed fusion process. These two processes are mostly used for metals. However, you can use for binder settings also, but for using some functional component, we mostly use this direct energy deposition or powder bed fusion process. So in powder bed fusion, basically, we basically spread a layer of powder, then we have an energy source on top of it, and that basically melts the powder wherever we want to make it solidify, and the rest will be as remain as a loose powder. Then once that layer is cured, then the bed goes down for the interruptions. So yeah, so I'm saying like we spread the layer, then we melt the using the electric layer of the powder is spread over one, and then again the same has been repeated. Like we melt the powder wherever it is required, and the batteries keep on going down, and like with a repetitive cycle we finally get the final component. So basically our final component will be buried inside the loose powders. So once it is done, then we can take out this, use the wire cut machines to remove the part from the substrate basically. Whereas in case of direct energy deposition, it is not like the same. We're applying energy directly into the feedstock material only. So that's why it is also called direct energy deposition. Like if you yeah, so if you look into this, like you can directly applying this laser, feeding the powder at the focal point of laser. So basically we're directly applying the energy to this feedstock material only. So different energy source can be used in DAG processes like laser, electron beam, or RD. Thing is that this laser is much more laser and electron expensive process. Mostly for laser the efficiency is like 30%. So which is like the remaining 70% of its energy we're wasting it as heat for a chiller. So same goes with the electron beam also, because we need much more energy to create the vacuum. Therefore, among all these, that is the most viable solution, because the electric arcs have like some power source have much more higher efficiency as well. So therefore, arc is mostly used. Similarly, when coming to the feedstock material, we can use the feedstock material in terms of powder as well as wire. When you use powder, so we can make very complex shapes, but handling the powder is quite difficult, and processing on the powder is also quite expensive. For example, if I say like if I need to buy some 1 kg of stainless steel powder, it will cost around 4,000 rupees. But same material, if I want to buy 6, then 400 rupees. So 10 times lower in raw material cost. At the same time, if you go the energy source also, the arc is also quite cheaper as compared to laser operating the arc. So this warm this all industries for making large components. Uh, not only that, we can footprint and we can enhance the life of a mechanical component. And since our energy and the raw material go to the mounted on the deposition head, hence we can implement multi-axis kinematics. This helps in making very large and very much complicated shapes without any support structures. It's not possible in power bed fusion. So only focus only. Among direct energy position, like I said, when you arc as the energy source and the raw material is in the is available in the form of wire, then wire arc additive manufacturing. So during WAM, we can use different energy sources like it may be gas tungsten arc welding or it can be plasma arc welding. So process is popular because of high deposition rate and across the world people are already using it. Like you can see there's a company called Relativity Space from US. They're already printing a huge rocket structure using this WAM process like you can see over here. Similarly, there are companies like Max 3D, MX 3D, they printed long bridge in Netherlands. Then there are people who have already printed some crane hooks actually in working condition because and these components are like they have very rough surface finish. So and this application doesn't require good surface finish. So directly you can use as a raw printed part in the actual application areas. Then in IIT Bombay, Sajan sir has already printed this kind of impellers, and he already demonstrated like we like around 60% material. Then we can make very complex with conformal cooling channel that component. So it has like half meter height. And here, if you observe that it's a tool part is quite noble, like we use a crocodile tool pipe. The one I am showing at the beginning, it's a jalebi tool pipe, something like that. So same tool part is used over here. And because of that, actually, we're able to deposit a layer height of around 6 mm high. So this helps in printing this entire big part in 20 hours only. Whereas if you want to print this part in maybe powder bed fusion or any other metallurgy manufacturing process, it would have taken like around 40 to 50, even some hours, even sometimes it's more also. So that's why this process is becoming quite popular across the world these days. Yeah, most of you already have seen or used warm process, but briefly I will tell how it look like. So basically, we have two units in the in warm process setups. Basically, one is our machine CNC head, which actually controls the motion. Like wherever we want to put the material, it will take to that position. And another is the deposition unit, through which we are melting the wire or the feedstock material, whatever, and it deposits selectively wherever we want to deposit. So, coming to the materials. So, in this process, we can use any material, any weldable material which is available in the form of wire, starting from low carbon steel, stainless steel, P91, tool steel, die steels, stellites, inconels, titaniums. So, lots of materials are there. So, those materials we can directly use in this process. And we can use different feedstock wire and the substrate or the pre-built layer. Coming to the gas tungsten arc welding, in the gas tungsten arc welding, like we generate the arc between a non-consumable electrode, which is usually of tungsten, and the substrate. And inside the arc, we fed the cold wire externally. So, like you can see, it's coming from a side way only. And similar goes with the plasma also. The only difference between the GTSW and plasma, in plasma, basically, we are creating localized plasma environment through which we generate the main pilot arc, which helps in getting a more constricted arc, which helps in getting very much high energy density at very lower current end. So these are some terminologies that are used in WAM basically. Like you can see the gap between the some variables basically, which governs the energy density in the substrate or maybe the part. Like if you have much high arc length, then you won't have much better control in the melt pool. So this every parameters actually matters a lot when you go for experimentation in WAM basically. And yeah, if you want to monitor the thermal profile and we want to measure the energy density, make it a closed loop, then you can use some non-contact temperature measurement devices such as IR camera, or maybe you can use even thermocouples also if you want to measure some localized temperature in the bed, something like that. Uh, Now coming to the gas metal arc welding, like I already said, it's the same and it's at a rate actually. So you can see in this image. So gas metal arc welding, basically, like I said, we generate the electric arc. So we need to connect to the two. We need to connect it to the plate. Like suppose one end into the negative terminal, one into the positive terminal. When you connect the electrode to the negative terminal, then it is called like direct current electrode negative. So in that case, electrode is at positive and the electrode is positive and the work negative. So in that case, uh, more heat will be generated when the more heat is generated on the substrate, like two-thirds of the heat substrate, because electrons are jumping to the feed. One-third of the heat is generated due to the kinetic energy penetration, as compared to like more metal will go inside the base above the substrate. While you go to the electrode positive, direct current electrode positive, so in that case, basically electrons are coming from the substrate, jumping from the substrate to the filler rod. So two-thirds of the heat in that case, because we want the wire to be melted. So therefore, we need high current in the electrode. And definitely in this case, you need to little bit play around with some parameters like contact tip to workpiece distance, arc gap, and the current and voltage, all these things, so that we can get an optimum pattern. Because this pattern should not be that low that it will come up with some small hammering only. So it has to be optimized. So usually it is preferred to be like around 30%, like the dilation basically, which is defined as the this height, basically layer height divided by total area of the layer height plus penetration. So that ratio is always preferred to be around the 0.3 for WAM basically. And but if you go to welding, then the previous one, this electronegative was preferred because we want more penetration in the base plate so that the bone become much stronger. So similarly, we have another option like alternating power source also, like AC current, AC power source. So in which half of the cycle of the heat will be generated on the wire and half cycle will be generated on the mostly used for deposition of electrode. So when we melt the wire, so we need to now the molten wire, the material has to be transferred to the melt pool or maybe the previously deposited layer. For transferring the material, uh, we find most of the metal transfers are there. So all these things are mostly governed by forces because the molten metal experience this kind of forces like gravity pull. Then surface tension always tries to keep the molten attached to the filler stock so that it won't fall down. Whereas there is drag force experienced from the atmospheric air, then electromagnetic force is also there. In this graph, when you keep on increasing the welding current, the mode of metal transfer is transformed from globular transfer to a spray transfer. Whereas when you maintain the welding mode, it's transformation. And so so when you go higher current, like you can see the material deposition and at much reinforced basically, they become much more predominant, resulting in more rotation. And another circuit transfer which is becoming much more popular, people are also calling it CMT also, cold metal transfer. So because of the low heat insulation, so that we'll discuss in the upcoming slides. So these are certain videos that demonstrate how the metal transfers are there. Like you can see in short circuit, the droplet is formed, then it's touching the mill pool and it's coming back. When it goes to globular transfer, you can see a droplet of metal is formed at the tip of the metal, doesn't detach till it reaches a limit after which it falls down. When you have spray transfer, you can see multiple small droplets of metals are being sprayed into the mill pool. Pulse spray basically vary the current between two limits like lower limit and upper limit. So during this upper limit, then the droplet is formed, and when it goes to lower limit, the droplet detaches from this tip of the it's a kind of sorry for the interruption on the internet. There is some fluctuation in the lab in the internet actually. Yeah. So in basically it leads to this kind of transfer mode, and this also depends on gas also, because like it's much more easily ionized, so you can see much more everything rotating transfer mode. So ideal and most of one process. Another goal method is actually invent first international it is a Australia-based company in 2003. It's the lower heat input. Like you can see, it is it will form a droplet on tip of the wire. Now, when this drop form, main current is now dropped to a very small, very nominal value. Say on like it is just enough to sustain the arc. During that time, mechanically we feed the wire with the droplet towards the male pool. It just directly touches short circuit. It takes back complex process. So it's always because so that we can eliminate those effect of such effects like gravity and electromagnetic force and viscosity, all these things. Uh, Another thing is like this Wi-Fi speed actually we can't vary randomly. This Wi-Fi speed is also actually synchronized with the welding current. Like the certain value of Wi-Fi speed, its corresponding welding current will be automatically adjusted into low, and your wire feed is high, then there won't have much energy available to melt the wire. There won't have much energy available to melt the wire. In that case, the unmelted wire will directly touch the melt pool without melting it. So which is not a desirable case for us. Again, it is not a desirable case for us. Again, if your Wi-Fi speed is too low and your welding current is too high, in that case, the wire will keep on melting and it will keep on consuming, and it this welding current will not be available. And if someone may be using some manual welding machine, that might not be available. Then in that case, experiment as well. Like you are varying the current, and you have to check in which setting continuous beat, and or unmelted wire issue. So that we need to check. Once we are done with the single bit experiment, now we know what is the height, we know what is the penetration. Like I said in the beginning only, the penetration has not to be too much high, just like welding, or it should not be too low that it will come up minimal one, and that can be get from the that you can achieve from this good one, because if its container is too low, then too high, then the issue will be like undercuts will be there, so those will act as the crack initiation. So based on this data, we will going to finalize a single bit this is single bit high data like high experiment. So basically in multi-bit experiment, we are going to overlap between the two bits, which is we call as step over. If it is layer flatness, and at the same time it also if your overlap is too low, then you can observe some underfilling at the center. At the same time, if the overlap is too high, then it will start bulging the material at the center, and at the same time it will also give some heat inputs and all. So that I won't discuss. I'm just focusing on this only. So you can see, like if it is too high, then the bulging of the material will be there. It will be optimized in such a way it will remain flat. But from this diagram, like if you observe this diagram, like if you consider the height as the h, and let us assume the overlap between these two beats is like p. So in that case, if the overlap P, and now if you observe this distance from A to basically B, it's nothing but half of P basically. You can see P by 2. And similarly, if you observe this distance like from A to F, it is nothing but half of the width of the beat. So therefore, it's W by 2. Now, if we want to get this area to be flat, I need to melt this material, bring above here. So this only will possible when this way based on weldability. We can use some differable weld bit also. Use material, but this argon actually creates issue. It doesn't have a cooling effect. The cooling cheaper. For the balance way is like mixing argon with the CO2. Keep sometimes 95% argon, 5% CO2. Whichever material you are using, high thermal conductivity material. And but most the most and but most the most effect of different shielding gas on the penetration. Warm basically, like you can see surface quality is the issue, then residual stress, distortions. So that need to be mitigated. So what we can do, we can for making parts. Then also warm is like not fine materials also. So those things we can there when it comes from repairing, if there is no weldability within the wire, if it's the wire being melted and base metal, so that may leads to crackings and all. So even there are some metal that need to be optimized during this single bit experiment, which will be which will help in reducing the porosity and lack of fusion in bead shape irregularities. That can be done in this single bit experiment only. This this for making some overing structures, supported structures basically, we need for making some overing structures, supported structures basically, we need coach some higher kinematics. So that we'll discuss in the upcoming slides. And higher kinematics. So that we'll discuss in the upcoming slides. And the most important issue that is been lagging in I won't been lagging in I won't standard procedures or certifications. Like we have the standards for any other manufacturing processes, but there is no standards, specific standards for or most focusly WAM also. We're following the same processes. So that might mean so that might mean sorry, the again my internet got disconnected. So discussing about so the standardization is not there. So if you can develop or you can work on some standardization for this very manufacturing, develop certain rules basically for analyzing these properties of these form components. Now, after here is like a basic experiments that we need to perform at the beginning whenever we have the machine. And these data, like I said, the single bit experiments, like we are going to or welding or maybe the voltage, whatever it is. So we're going to vary alternatively, what is the layer height, what is the penetration we're getting. Similarly, for step over also for different toolpaths, we need to do this multi-bit experiments, and those data also keep on collecting for different process parameters, and you'll keep on collecting. And those data, which is those libraries, then we need to use in this computer process planning. So before starting computer process planning, we need to computer process planning for WAM. Computer process planning basically. So basically, process planning is nothing but the sequence of operations that we need to perform the raw material to convert it into a final finished component. So if you perform this operation with the help of computer, that is called computer-aided process planning. For example, suppose I want to make this pen. To make this pen, what are the processes I need to make on the raw material, which is nothing but the plastic. So after converted plastic into finalized shape, that is called the process planning. So so this is the typical process flow of basically a worm. So you can see it starts from the CAD model find out an optimal wheel orientation so that it will require the minimum, or in other word, we can say it will require minimum energy, not necessarily support. So we can create a single goal only. Then if it requires, sometimes then we can calculate support, but that is not. It's very rare. Like no one prefers to use support structure for metals, specifically in DED. Then we need to do perform slicing. After slicing, we need to perform the tool generation for each slices to post process to generate a single ANSI file. That ANSI file we need to put to the machine, and then finally we'll get the final component. The current issue with this exit CAVP solution that are available in the market is that most of the CAVP are limited to STL file format. STL is like stereolithography, and sometimes it is also termed as standard tesserated language. So this STL actually we represent the entire model with the help of triangles. So therefore we can say we won't be able to represent exact circle with the help of STLs because it's impossible, because we will always have some polygon only. We can't get exact circle any. So that is the issue with the existing CAP solutions available for WAM. Apart from this, we can say access to the process parameters, like step over angle, step over distance. Like I said, this actually varies from machine to machine. Like if you're using, may suppose Lincoln power source, and I may be using Furnace power source. So the same current and same heat input may not give the same beat. It's good idea to it's always good to have the access to these process parameters like step over distance and not only that, even this exists some standard tool paths, and those tool I can say like those tool paths are even for traditional machining tool path like zigzag and all. But since we are not using whatever it's available, so that's why people are mostly using this zigzag and all. But if you observe there are available opportunities there in creating your own tool paths and all. And another thing is the conformal slicing. So that we'll discuss in upcoming slides. Like why need to slice always horizontal? We can slice in conformal view also. Suppose something is growing conformal to a vertical, we can slice in such way also. That we'll discuss in the upcoming. So the entire CPP for WAM we can classify it into three categories like pre-processing, then processing, and then post-processing. In pre-processing, basically it starts with like CAD model preparation and it's finding its optimal build orientation. Then CAD model modification if sometimes required to sometimes requires like some portions may not be required to be printed. Like say this is most focus on circle or ideas who are designed for the manufacturing approach. So those things we can perform at the pre-processing stage. Then we do slicing on of the parts. Then slicing basically we need the data. So like I said in the previous slides, we need to generate an bid library. From the bid library only we're getting this slice. Like I said, from multi-bid particular tool path. So if you're choosing and from single bid actually we observe that zigzag tool path is giving a layer height of around 2 mm. So then I will slice according to 2 mm to this one. But at the same time, if same part, if I need to print it with some another tool part, like I said, like some crocodile tool part, novel tool part, which gives a layer height of the 6 mm, then we have to modify the slicing parameters over here only. Then at the same time, we can also splitting in such a way like selecting the substrate also. Say suppose what is the optimal size of the substrate. It not necessary to be, it has to be bounding one. Like it may be we can use even smaller one, or sometimes it may use some bigger substrate also, so that you don't want the part to be warped. Or then we can calculate the G code for this tool patch, like the trajectories we can calculate. And yeah, so before calculating the trajectory, we need to calculate a step over. So this experiment we have already performed in a multi-bit experiments. So those data will fed into this process parameter over here. And then we need to set the process parameters in the welding source. And yeah, sometimes it's required to preheat. Say suppose you're depositing certain material. Say suppose you want to repair some cast iron, something like that. So there we need to do some preheating. So those tool path for such things also plan at this pre-processing stage only. Like maybe in we are just moving the gas welding gun or something like that. Some heat source we are just moving only the heat source. Nothing is there. So that you can preheat the substrate to some temperature like 300 degree or 400 degrees Celsius, something like that. So once it's heated down, then we're going to deposit the main material. So those planning, those toolpath strategies that we can control from this stage. And in during in situ processing, sometimes it's required to be like preheat using some laser source like hybrid process. And sometimes it make to do the phase milling also, because this oxide layers keep on accumulating at the top of the deposited layer. So which become much harder, and some therefore after few layers, someone may need to perform phase successive layers of these oxides. Then people sometimes do ball burnishing. So process will come under this in situ processing. Then we may need to the final finish. Yeah, then we can plan the substrate, and if required, then we can do some heat treatment, then inspections, and final finish parts. To get the final finish, we can perform some final some other post processing also. So so process planning for such operations will come under this post processing for CPP WAM. Now, we are proposing over here like to use a CAM software, which is actually already existed in your universities or colleges, and it's mostly used for process planning of traditional methods, say suppose milling or something like that. And same software we can use it for warm process, or maybe hybrid warm process. So how to do so? That we are going to discuss in this session. So, before going into the starting the software, so we need to satisfy certain operations, like certain, I can say, uh, certain requirements need to be satisfied uh, by the basically this CAM software. So before I start it, I would like to ask like if you have any doubt till here, anything, are you able to follow like how we do single bit experiment, why we do like in any query till here, like how we identify those process parameters and all. Okay, okay, fine. Then I assume that without in till here. Okay, so
Participants may choose to unmute
yeah,
themselves or they may write their query in the chat box also.
yeah, you can write in the chat box also. Anything like any doubt? Suppose you have one welding power source that you want to that make it as a warm process and you want to start some experiments, and also you have any doubt in till that, you can just let me know. Like you can just ask me over here also. Like which gas to be used for which material and all. Okay. Uh, okay, then I assume that it's well, it's going well for you. Like it's you have the follow up till here. CAM package that is being used for existing used for machining process. We need to those already on any everything space. Like you can see over here. So and it should be like any in the space, not from the origin only. It should be any place on the entire space. We should be able to generate a plane. The next is like the CAM software should have the capability of basically performing Boolean operations like intersection, then union and all that. It should be capable of performing those operations. Then the then this all CAM software should have a capability of performing basically slicing like basically it's like after slicing we need to offset it, so it should have ability to perform curve offsets, and the offset also shows the direction. Like you can see, if I have this part and if I slice it, so I can get two curves, like one is corresponding to the hole and another is like corresponding for the outer surface. So then I can accumulate the material for machining, for final finishing of it. So therefore, I need to keep some extra material. So when you look in this part, so my this outer curve has to be offset outward because I need some extra material from the outside the surface. And if I if I want to keep the machining allowance for the inside also, then I have to reduce the hole diameter basically. So I have to offset the curve corresponding to hole towards the in basically. So that is called hierarchy basically. So how to do so? So say suppose I can show you like you have this curve. Basically you have one slice over here. So can anyone tell me? Like maybe you can write also in a chat also. So in this case, my internet was interrupted. Uh, yeah. So yeah, I was just asking like if you can even write in the chat also. So can anyone suggest me? So where to offset this curve one in inward or outward? Maybe you can write in the chat also. Okay, fine. Yeah,
Sir, I think
anyone?
there is a problem that is coming in your voice. The
Okay, okay. Is it coming now? Is it fine now?
Sir, at times it is coming, at times it is not.
Okay, okay. Okay, fine. So things like in this diagram. can you we need to offset this curve number 5? Should we go inside or should we go outside?
Sir, just
You can write in
try.
the chat.
Sorry to disturb you again, sir. So your voice is
Yes, sir.
being disturbed. You can try without camera if that works.
Okay, 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 sure, sure, okay. Okay, so good. Okay, okay. Thank you. So yeah, you can run a chat also. Like in which direction we need to offset this curve, like curve number 5, if you want to keep the machining allowance. So can anyone tell in the chat? Okay, fine. Then maybe I will tell because yeah. Okay, fine. I will tell. Yeah. So if you do contour offset, then you can see the curve that is corresponding to your outer surface. It's going to offset in the outside direction, and this red color one represents the hole basically that need to be offset inward so that I have extra material so that I can drill the hole again. And third one is like this island, the center portion. The island is like it's having some material, so you have to keep it extra. And where there is no material, that I have to keep again reduce the diameter, like says increase hole, something like that. So like that we need to offset it. So to do so, we call it hierarchy identification. So how can you do so? So basically to partially sort all the, because basically we have the information on all these contours, then we sort all the contours based on the area, and then you can say that the biggest area is carrying all the curves. Then after that, we are going to again sort based on this area, carrying the other small part, something like that. Then we will check the coordinates of this small point maybe, and we'll check if this point of this coordinates, we will use this polygon test, something like that. So by performing operations, we can figure it out like which portion is whole and which portion is the main material. So that we can perform with the help of this hierarchy study analysis basically. Then the next thing is like there should be an interlink between the CAD and the CAM system, because the slicing actually comes under CAD operation, and the toolpath planning and toolpath calculation, all this comes under CAM package basically. So therefore the CAM package or the CAD package that you are using, both should be able to communicate with each other. Like maybe you can use the CAD, maybe AutoCAD maybe for your CAD operations. Then you may use maybe Power Mill or maybe Fusion 360, and because these two have some links with this, because both are from Autodesk, so that link you need to establish. But in most of the cases, it's already there. Like say suppose SolidWorks have already CAD and CAM in a single platform only. Similarly, Mastercam also having CAD and CAM single frame only. So basically that thing, that integration should be there between the CAD platform and the CAM platform. And the next important requirement in the CAM software is basically it should be able to generate different toolpaths for a given contour. Not necessarily toolpaths like zigzag, contour parallel, or honeycomb, something like that. It may have some other Hilbert or Crocodile or something like that. Some other toolpaths uh, can also be used in this should be present in the CAM software. And then once you basically generate a toolpath, then this toolpaths directories we need to convert into G code specific for a particular machine controller. Say suppose you with a some Siemens controller, Then I might be having a I might be having a CNC machine with some hash controller. So, and every machine understands some defined file extensions. For example, this CMS understands .mpf extension file on G code only, whereas Fanuc understand .nc, then Mazak understand .ppf, and Hash actually .tap or sometimes .hash. So define controller users defines in this extension. So based on the controller that is available with you, it should be able to post process the data accordingly. So therefore, that CAM software should be able to should have wide variety of post processor options. uh, and yeah, then and specifically like the machine that the control that being you are using, it has to be present in their CAM software post processing module. Then finally, uh, it should have an feature application programming interface, or sometimes it is called as macro, because we are performing the same operation only, like during additive manufacturing, we do slicing and toolpath generation. Basically, it is the same thing only. We are like we are repeating same thing for different heights. So it's a repetitive process. To make it as a complete automation, we need some tool called API or application program interface or macro to make it much more automated one. And the fourth important thing is like post processor modification, because that's since the CAM package basically things like we are doing basically machining. So, but the thing is that in actual we need to start we're doing deposition, and we need to also use some commands to trigger the welding process, to start the welding process. So therefore we need to modify the post processor. So how we can do that? So basically when you generate the tool path, we can set the RPM to be 0 because we're not doing machining, and check in the XC file that has been generated from the basically this CAM software, and it will give the unknown. If it is 0, then we'll understand that this is actually a deposition process. And if it is not, then we'll treat it as a milling process and we'll use a standard post processor. If it is zero, then we'll search for the cutting move, and wherever there's a cutting move, say suppose Z01 or Z02, before that one, we're going to use the command that is used for the welding start command. And then we'll say suppose in our case it's M51, like use the M code of M51, which basically triggers the this sorts a relay, and which in turn triggers the welding process. Similarly, M52 command we are using over here to stop the welding process. So next is like we have to use this command before the toolpath for rapid movement like G0. So therefore, what we will do, we will first we will store the sequence number wherever you observe this cutting movement. So after that, we are going to our M code, which is corresponding to deposition process. Then we'll keep on searching for the next G command, which is a rapid movement. So wherever we observe some G0 command, just before that command, we're going to use the M52 command. We'll just stop that welding process over there, and then again we will go for search for another cutting movement, and we will keep on doing this until we over all the sequence number of the entire G code. So now I will show in the PowerShell and PowerMill how. So is there a doubt till here? Any query or anything like that? You can write in the chat, or maybe you can raise your hand also. Okay. Okay, fine. I just assuming that it. So now I'm going to give you a demonstration on this software, how it works basically. So before that, I will just tell you what we are going to do. Just the overview of this entire framework basically works. I hope my screen is visible to you. Okay, so yeah, so first what we're going to do, we're going to import the CAD model, then we're going to create one slicing plane on bottom of it, then we're going to perform the intersection between this slicing plane and the CAD model. Once we get the slice, the next thing we're going to do is like we're going to offset the curve. Like say suppose for that I already discussed in the previous slides. Like if the curve is corresponding to outer surface, then it will be offset outward, and if the curve is corresponding to inner surface, inner feature, then it will be offset inward. Then for this offsetted curve, we're going to generate the deposition toolpath. This offset actually we have done as per the machining allowance, like how much machining allowance you want to keep for deposition basic for final finishing process. Then we can, if required, we can also add the face milling tool part in between. Then once we are done with the face milling tool part, then next thing is like we are going to extrude this offsetted curve by the layer height, and we're going to move the slicing plane by the layer height, and the curve will be offsetted as per the machine elements, and the entire process will be repeated. So this extrusion is that we are considering over here. This is actually when you're going to generate the tool part for the final finish milling. So basically, when you're done with all the slices, so all the tool parts are generated, then the offsetted model we can use it as a raw stock basically for the finished machining. Because if you directly consider the machining to be taking place from a uh, rectangular block, it will look something like this. Like there are lots of air passes, which are not a good idea. Like not only the build time will be increased, it will also affects the not only build time, but it also affects the basically the entire cycle of production also. So it's a very unproductive process. So those things we need to eliminate it. To do so, we will going to use this extrude model. So basically, this extrude model will tell the software that this is my raw material. From this raw material, I need the final finished part. So if I tell like that, now the software will generate only a tool part which is necessary to get this final shape. So this is once we get the final, it may be in a single file only, where maybe we can use it for at the beginning we're going to deposit, then next certain sets will be like face milling, then depositing something like that, and towards the end maybe we can put in a single file only, we can put the final finishing operation. So this will help in getting the entire process in a single NC file, and this is basically helps in we don't need to available keep on standing in front of the machine. We can put it on the machine through a USB stick. You can start the building or the process. Basically, you can just walk away from there. You can do your own work, and it will be keep on depositing. And after depositing, it will keep on machining, and so everything can be automated. So this is the brief idea of like how basically this algorithm works. And yeah, so this is some part that was demonstrated. Like you can see, so we set a framework, like how to like we have used a master temp to print this part a build like structure. So you can see we deposit the we basically create the CAD model, and then we kept the machining allowance on mm. So when you compare with the scan data, that we have scanned using an laser scanner, so you can see the mean deviation is like around mean difference between this CAD those 2 point cloud is like around 0.968, which is quite around like 1 mm. And this small issue deviation is like maybe because of some distance issues. But anyhow, whatever machining allowance I'm putting, the same thing I'm getting in this in this compare software. When you deposit the part and then you check it, so you can see actually you're getting a similar excess extra material. Like you can see 1 mm extra material we have. Then finally, when we do the finished machining, you can see after performing finished machining, so the mean deviation is like around 40 microns. So even this can be further improved if you use some better cutters and all. So like this, like you can see, we can perform these kind of operations, and you can save lots of time in finishing finish milling also, as well as material also. Because if I need to make this part in traditional method, I would have taken an a cylindrical bar from which I'll dig out the material and finally get this shape. So in that case, the wastage will be too much high. So now I am just depositing this extra material. From here, I am getting the final shape. So wastage, as we have calculated, it was coming uh, like we are only 40% only, and for this particular case, and the build time is drastically reduced. Like that will be build time is reduced by 90% as compared to complete machining. And yeah, someone may think of this making this part out of casting will be much cheaper one. Yeah, that's true. The casting will be cheaper one, but that is true only when we are making some when we are making some mass production. Let's say suppose 10,000 piece, 20,000 piece, something like that. If you're printing maybe 10, 50, or maybe 100 also, then also casting cost is not that much justified. And also the defects and all those are like some other aspects that also need to be considered when you're going for like choosing this manufacturing process. So yeah. So now I will just show you how we can use this power shape and power mill for toolpath planning for one farm, or more specifically for hybrid farm. So yeah, so I am going to launch this power mill. So okay, I'll just remove it. Yeah. So this is the power shape. The power shape is nothing but it's a CAD software where you are going to perform all the slicing related operations. And this is the power mill. The power mill deals with all the toolpath and all the basically toolpath and all NC code generation operations are performed over power mill. So and it not necessary to be its power separate power mill. You can use your other software also. Like I said, we have already used this framework in Mastercam frameworks. Then right now we are developing this for Fusion 360, and we have already done with SolidWorks as well. But mostly we have used SolidWorks for 2.5 axis. So the operations will be completely same for any CAD package, CAD CAM package basically. So you can see this is GUI. So at the top you can have this menu bars where you can select different menus like home, then work plans. If you want to perform some 2D operations that you can select from here. Then third one is like solid, like you can create some solid model. Like it's not necessarily like you have to create the CAD model outside any other third party environment. You can create the CAD model here also. For that, you can have this all these solid commands like extrude, revolve, cone, and all. There's a primitive shapes also available. Then we have this surface commands also. Like if you want to modify or create something surface profile, then you can do some assembly over here. Then you can do some manipulations of the created or maybe imported models. There are some wizards for imported one. You can even visualize wherever the undercut is there, then all these things, how much material is left, all these things you can analyze from here. Then you can do drafting and all. Then yeah, then finally you can also see refined views like in which you want to see. So those things you can see in this menu. Now maybe I'm going to create one part. Maybe I'm going to make one solid. So before I start, we need to create the work plane. So this work plane, you can just go to the work plane and create work plane, and I can just write over here 0, which is nothing but my global origin. So this work plane has been created at a global origin. So now I need the, so say suppose I am getting maybe this cone. So if I click over here, so my cone has been created. So let's modify it and make it a little bit bigger one. Mm, yeah, this is like 50, and this is also like maybe 100. That's too much, maybe 75. Okay, fine. So maybe I want to print this part. So like you can see, either I can make the part over here, or else I can directly import the CAD model inside this platform. Now the next thing is, like I said, we need to create the slicing plane. So since plane is a surface only, so we can go to the surface, and there we can select the plane. So before selecting the slicing plane, we need to ensure that the part is aligned in such a way that its z-axis is the torch approach axis, and all the portions should be reachable from this z-axis perspective. Then from top side, I can make this part. But if it is like rotated one, maybe I can show you. Edit, rotate. I can select the axis. Yeah. So maybe if it is like rotated in some angle. So if it is like this, now you can see over here my z-axis is actually from the top, and in that case this will be an overhang. So this is known, and this will require support. So it is not a good idea to print this part in such way, in this way. So the best idea is like I can print in this particle direction like this. So therefore I have to rotate it. So if it is not in the part, then in not in accurate position, then I will select it. Then we'll go to rotate. Then we need to select the axis. So right now, if I rotate about y-axis, it won't help. I need to rotate about yeah, yeah. I need to rotate about x-axis. So I'll go to x, and then rotate 90. Minus 90. Okay, I need to rotate about y-axis. Yeah. Mm, that's nice. Yeah. So yeah. So now it's properly aligned. Now my Z is coming from top. So now I can print this part in a single go only. So how to choose the axis? You can select from here only which axis you want to draw. So you can choose over here. So currently I'm choosing this Z, and yeah, now I'm going to create the slicing plane. So slicing plane we can create from the surface. If you go to surface and click in the um, this option called plane, then you need to click the center of this work plane. And once you create it, the plane is created. Now I can double click it, and I can adjust the size, maybe based on the model you're using. Say it's quite big part, maybe 1. Yeah, just some extra material, some extra clearance will keep from the model. So how can you calculate it? That is possible from a option called bounding block. So that actually comes over here. So when you select the model and you create the bounding block, it will tell the maximum and minimum of the part. Like so, in this case, if you select and you create a bounding block, the bounding block will be like around it's around this border only. So from there, you can extract the x and y and z coordinate of the maximum x, y, and z coordinate for this part. Then according to that coordinate, if I add some clearance of like each axis, then on basically in x and y, I can select the exact this slicing plane. If my plane is smaller than this part, then I may lose some information of the final CAD component. So final printed component. So therefore, we need to keep some extra around this slicing plane. So now this is a slicing plane. So now I need to move this slicing plane by some layer height. So for that, we'll go to move, and I want to move it in Z direction, maybe by maybe 5 mm, and then I'll click OK. So you can see it's moved by 5 mm. And then if I go to the wireframe, so basically I need to perform the Boolean operation between this slicing plane and the CAD model. To do so, we'll go to wireframe. In the wireframe, there's an option called uh, intersection curve. So we are going to select this intersection curve. Now it's asking me to select the primary and secondary object. So primary, let's select this the CAD model one, and secondary, let's select as the slicing plane. And then I will click OK. So it will generate this slice. So for power save, it will generate the wireframe. So but in defined CAD packages, it will come under different tools. Say suppose if you go to SolidWorks, it's coming under sketch only. Since the 2D operations, so any tool that is used for 2D operations like drawing a line and all, so within the tab only we'll be able to option. This is intersection between a curve and a plane. So right now we have performed the slicing, but that is not visible, right? So, but if I hide this one, now you can see, right, this is one line. So you can see, right, this is a slice. So not only this, even I can do one thing. Maybe you can create multiple slices in a single go only. Say suppose it is here only, and now if I go to this edit and move, and I select the slicing plane and activate it to the z-axis. And now if I specify the layer height to be say suppose 5 mm, and I enable copy, and I'm increasing the copy maybe 10. It's not selected. I'll just select once again. Yeah. Wow. Plane is selected. Now move. Now I want to move in Z direction and select 5 mm. And the copy is maybe this copy is maybe I can calculate maybe 10. Yeah. Okay, fine. So you can see these are nothing but slicing plane. In a single go only, I can generate this slicing plane. I'll click OK. And now in a single go, if I go to wireframe and if I again select the intersection curve, so first I need to select all the slicing planes, go to intersection curve, then we're going to select the model and I click OK. So in a single go, now we are able to make the all the slices. You can see, right? So all the slices are created. So using the API, so that we'll discuss maybe towards the end of this session. So now I just want to interested in showing how it works. So I'll took only one slice only. I will take this one slicing plane and I will take the intersection between the slicing plane and the curve and the model. Yeah. So now I'll just hide it. Now you can see there's a curve we have obtained. So next step is like I need to offset this curve based on the machining allowance. So for offset also you can go to this edit tab. So in edit you can see this option called offset. So in offset you can see this arrow is directing towards outward. So the direction is correct only. So say suppose I want the offset to be maybe 0.5 mm. So I'll keep zero point 0.5 and click OK. So now you can see, right? So I get another curve of this one, which is 0.5 mm from distance from the main curve. So I'm interested in this curve only. So once I get the slice, the next step is like I can select this entire slice model, and then I can send this data to Power Mill. And this is why that one condition was there for the CAM package, that your CAD software, basically CAD platform, should be able to communicate with the CAM software. So in our case, this PowerShape is a CAD and PowerMill is a CAM. Now I'm communicating from the CAD to CAM by clicking this button. So now if I see over here, so you can see one plane come over here with these curves. Okay. So next if this is like I need to generate the tool part. So creating tool path, maybe I can select this curve. First, I need to create the boundary. So I'll select this one. I will create one pattern. And inside the pattern, I can insert the model over here, insert, and you can go to this model. And if I insert it, and if I hide the layer, then you can see this is a slice, main slice, and this is the slicing plane. But that is not of my interest, so I'll delete it, and I'll keep only the outer slice only. The inner slice will I will deleted it because it is not necessary for deposition. So now I have this sliced contour and this slicing plane. The next step is like I need to create the tool path. So for creating the tool path, again we need a tool. So first we'll create a tool, and it since we are depositing, so it can be anything. Maybe you can end mill, you can put ball nose mill. So I'm choosing ball nose mill. Then here you can need to define this dimension. So this is nothing but your you can consider it to be the wire diameter, whatever you're using. Say suppose one, and this might be you're thinking as a stick out length of the contact tip, maybe 5 mm, something like that. Then for better visualization, you can add the shank and all. Maybe you can make it something look like actual your nozzle, so that you can helps you in identifying how much collision, how much safety distance is there between the part and the model. And yeah, you can just specify as per your nozzle whatever you have. Then you can put maybe holder also you can put over here. So yeah, so overhang is like maybe zero, yeah, 20. Okay, so you just like this, we can just make it something look like a welding torch or something like that. Maybe this will be like around 60. Yeah. So now this is something look like my welding torch. Okay. So you can see this is how this torch look like. Now I have the torch specific tool. The next step I will be required is the basically a block, because I know I'm doing deposition, but the software doesn't know I'm doing deposition because it's considering it as a just an milling operation only. So therefore, I have to define the raw material for this milling. So for that, I need to select the model, and then if you go to the create block, directly click over here, popped up this window. So there you can directly click it. So automatically it will form the bounding blocks. So from here you can actually you can extract this from sort of slicing plane, like how much bigger slicing plane you require or not. So these things you can do from here also. So once it's selected, you click accept, and yeah. So now block is defined. I have the work plane defined, and I have the model, which is I have to do machine, obviously deposit. So next step is like I have to create a tool path. So we'll go to the tool path and create a new tool path. So in a new tool path, basically it will come something like this. And since we are doing 2D operation only, I'll go to finishing and say suppose it is like, let's assume it is raster finishing. Click OK. So then this menu will pops up. So let's go one by one. Initially, the beginning it is like the work plane. So work plane is one. That is nothing but the one we have defined in PowerShell at the beginning. The same work plane is just being called over here. Next are block. So block is also we have already defined. The third option is the tool. The tool is also we have already defined. You can see it's like how it looks. Yeah. So you can see this is a tool. Then the machine tool is the accelerator. The next thing I need to define is the boundary. So let's not select this boundary. We'll do it later. Then you can go to the raster finishing. Here you can see the angle. If it is zero, then you can see it will create the full path something like that. But if you keep it like 45 degree, So you can see zigzag lines will be turned around like something like this. So best practice is like we need to keep on rotating this angle at each layer. So that is the best practice because if you all keep the same angle for all the layers, so there is a high chance of material being dripping after some layer because towards the end it always creates issues. So therefore always you need to rotate it by 45 degree or 90 degree after each layer. Then next ordering. So here we need to select two-way joint. So because that will create a connected one. And since this software is actually uh, interpreting data, so we need to specify the arc radius between 2 points. So you can put it as value something like that. And then here you can see the step over. So this step over is nothing but a value that we are obtaining the optimal capacity we are obtaining from the multi-bit experiment that we have seen in our session. We are going to select this step over value be same. Say let's say the phone right now we keep it like with 3 mm. Then and it's fine. So now these things are like mostly related to the machining process, so we don't have to worry about much. The non-process is the point distribution. So here we have to redistribute the point. This is because if your contour is having the slice contour is having less points, then during today's session it may lead to some over-depression or under-depression towards the point. To eliminate that, we are going to generate lots of points in this outer contour. Then once this is done, then next is tool axis. So for a time being, I'm just demonstrating for 3 axis machining head or deposition head. It uh, so yeah, so basically, this tool axis is like basically providing a single 3 axis strategy. So that's why I'm keeping it vertical. But since dealing with DED, so you can use some other uh, so like maybe you can use maybe multi-axis tool like lead lead, correspond, so other options are there. So we are going to select accordingly if you're going to keep some complex step like that. Then next thing is like machine not important uh, the repeat height. Like want the tool to be move at a faster rate. After that, it will go at a very slow plunge feed rate. So that can be done from this rapid TRS, rapid height basically. So if I keep it like let's suppose right now keep it 7 only, 10 only, and result not required. One thing that's important is lead link. How it's going into material and how it's coming out. So in our case, it's fine. It's nothing. But if you're doing some multi-axis, then internally keep it as normal arc, something like that. So since our case is just normal 3 axis only, so I'll just keep it as none only. Then lead those things. Then we can specify the start point as well. Like we can specify the start point maybe at the first point step, or maybe we can specify the block center point. So let's keep it the first point step to reduce the excessive build time. And we have endpoint that is also fine. Now in this tab, coming to this speed and speed, here you can specify the deposition speed and speed. Like I said in the previous slides, that we need to put this thing as zero, frequency field is zero, because the post process that we have created in such a way that whenever the speed is zero, it will come to know that this is deposition process. See, like, and this is the plunge speed. Plunge speed is like at what speed the tool is plunging inside the. It's not depositing material, not depositing, so using the depositing material, not doing machining. Therefore, the punch speed rate can be anything. Because during machining, if you keep a high punch speed rate, in that case, there's a high chance of breakage of tool teeth and all. So to avoid that thing, we keep it low value during machining, but since during deposition, so we can keep it high also. Maybe same as cutting speed, which is deposition speed. And there's one scheme fee that is there. Like during machining, so the deposition, uh, if you want to work from very rapid speed only, so wherever a distance is long, so not on a certain field, then it will go very slow speed. So that speed is nothing but is speed. Then again, we are doing this deposition, so we'll keep it as it is. We'll click calculate. So one thing you can see over here, yeah, you can see it has been created for the entire slicing plane. Now that is not required, right? We want to generate the toolpath for inside only. So for that, we need to define this limit over here. So if I go over here and you create an user defined boundary, so there you can select the pattern that you've already set created at the beginning of this boundary. I'll click accept and then click calculate. So okay, and to create the boundary, again, I will just create it. I will just copy this pattern and I will just paste it as a new boundary. So now new boundary has been created. Now I'll go to setting again and go to the boundary and you select this one and click calculate. So you can see now toolbar has been generated. It's been generated and this height you might be looking at it too much high. So maybe you can again reduce it. But this will come under the beginning only, that is the start point. Yeah. So yes, if maybe like a little bit, you can see it starts from very low. Then you can just say whether it's working fine or not by going to this tab called simulation, and you select this tool path, and then you keep play, so you can actually visualize how it's going to deposit, how it's going to move in your machine. So it's showing a simple part. But what if into this toolpath or making some some component? So in that case, um, if you have other parts to, so where your torch is calling on those parts, that you can actually visualize over there only before going to the actual machine. So this is a very kind of camp soft, basically camp software. So yeah, you can see like this. And when if there's any issues comes, then you can check over here also. It will directly show if there's collision or not. So that will show over here. So I hope after this is clear, like we were able to get a toolpath. Okay. So next step is that we have the toolpath trajectory. Next step is like we are going to convert this trajectories to a G code basically. So we're going to click on it and then we're going to click as your create individual entity file. Once you click, before that one, I'll just show you the exact angle effect. Just go over here. So when you go to this this is zigzag finishing. So here you can see the angle right now is 45, but you can just alter it to maybe 90 or maybe 135. And even you can select the start point also. But it was right now it is a lower left at this point. So I'm just changing upper left, and then I'm going to again recalculate. So you see from here it is just showing the tool part. And if you go this one and just play around, then you can see how it's going on. You can see it's about small parts sticking up and coming down. So this is actually happening because of this repoint issue only under counter only. So then for this slice contour, we need to get with more number of points. Generally, it works perfectly. So once it's done, next is like if we right click on the tool part and you can go to the create individual NC file. So now your NC file is over here. If you right click over here and if you go to the settings, so then this window popped up. So here you can write maybe maybe here I can write about other things like maybe tool part name and all. Just just sorry for the interruption. Yeah. So actually here you can directly specify the tool part name over here, maybe tool part. Then you can specify where you want to keep the tool part, and maybe I can keep it in the current desktop maybe, and I'm writing maybe one. Save. Then we can select the next is the full thing to select when you are depending upon your controller skill. So maybe you have some hard controller or something like that. So in our case, I have Siemens only, and accept it. And then rest is like fine, like this apply and write. So now it will automatically write the NC file on it. So you can see it has been created. So I'm showing this toolbar has been posted. So if I go back to the desktop, so you can say this tool has been created. So if I open it with the help of an press on this symbol, you are actually able to see the G code that is corresponding to the thing. You can see over it. So it's all it is. Okay. So now the next thing, like you need to put M51 as a well done for every Z01 command. So you are pressing zero once, here you need to put M51, which is nothing but my weld on command. So yeah, so and for example M51 Z01 one. Okay. Like this, you can set over here, and similarly, I'll search for the next. Before that one, I'm going to add M52 to stop the welding process. So like this, you can modify the NC file. I hope it's clear to you. So okay, maybe we can take an half an hour break from here, and remaining maybe we can discuss start discussing after 4:30. If you have any doubt till here, you can still ask in the chat. I mean, ask also. I am here only. Else we can go for lunch break maybe about 30 minutes.
Hello. Am I audible? Sir, am I audible? Ritu,
Is it okay for you? Yes, sir, you are audible, sir.
okay, now we'll be
Yes, yeah.
having half an hour break, and after that we'll join by 4:35.
Okay. So let's say 4:35.
4:35.
Okay, let's 4:35.